Good morning, good afternoon to all from the editorial board of BuildUp portal. For the ones who are attending a BuildUp webinar for the first time, welcome. For our returning audience, thank you for renovating your interest. Just a brief explanation of what is BuildUp. It is a collaborative platform in the field of energy efficiency in buildings. It is continuously updated and it represents one of the key sources of information on the topic of energy efficiency. You can register and become a member of the community, and you can also upload news, events, present a case study, results from a project, and so on. I would like to invite you all to navigate the portal. In the Learn section, you'll find all the podcasts of the past webinars, so it is possible to listen to all the previous presentations. At the end of this webinar, the link to the full presentation and the file to the PDF presentation will be made available in this section. It is a pleasure to host today's third webinar on the EPB Standards series entitled How to Make Good Use of the Outputs of the EPB Assessments, which is organized in collaboration with EPB Center and RIVA, Federation of European Heating, Ventilation and Air Conditioning Associations. As you can see from the screen, we have scheduled a series of webinars on the topic of EPB standards. Take a note about the next webinar, which will take place on the 26th of May, and which is entitled EPB Standards, Hourly versus Monthly Method. I would like to invite you all to contribute and participate in this webinar. You can ask questions by typing in the box on the right side of the screen. They will be answered at the end, after all the presentations. Now I would like to present the agenda of today's webinar and introduce the two speakers. Dirk van Orshoven, Independent Energy Engineer, and Dick van Dijk, EPB expert from the EPB Center. Dirk van Orshoven will make 3 presentations, and he is the one who will start by giving an overview of the relations between buildings and product standards and regulations. Then he will discuss how to tailor EPB requirements, and his final presentation will be about partial EPB requirements concerning the fabric and the thermal energy balance. Dick van Dijk will make 2 presentations discussing features, indicators, and requirements, and finally EPB rating and certificates. Now I would like to leave the floor to Dirk van Orshoven. So please, we can start the session.
Hello everybody, also welcome from my side. So I will give an introduction with an overview of the relation between the building standards and regulations and the product standards and regulations. As Julia also already said, I work as an independent engineer with a focus on the EPB and by extension energy efficiency and sustainable energy in general and other energy issues. I've been intensely involved in the original development of the Belgian EPB regulations, starting more than 20 years ago. I was also involved in European projects on the EPB called ENPER and ASIEPI, where we exchanged a lot of national EPB information and sought for optimal solutions. And I've been co-author of the 2 standards that are the topic of the webinar today. I try to move to the next slide. Okay, here we go. So standard EN ISO 52003 consists of 2 parts. The first part is the standard itself, and it discusses the general aspects of indicators, requirements, ratings, and certificates. And the second part is the technical report, which provides further detailed explanation on each of the topics. This schematic shows the position of what we call this post-processing. Generally speaking, we have the totality of the EPB standards, for which the overarching standard 52000 provides the overall architecture. And we see that in the simplified scheme, based on various inputs, first the energy needs for heating and for cooling are calculated, then the system are taken into account with their efficiencies to obtain the final energy use, which is converted to primary energy use and aggregates to get the overall energy performance indicator. So this is the technical aspect of the calculations. But after then, to use these indicators into the regulations, the regulators have to define requirements and ratings, and how to do this is discussed in a qualitative manner in the two standards that we will discuss today. And so it's post-processing, it's after the calculations are finished, how are the results used in regulations that are the topic of these two documents. I would like to give a preliminary warning to avoid any misunderstanding. So these two documents make the link between the EPB assessment standards and the regulations. But all these regulatory matters are, of course, the sole responsibility of the public authorities to take all decisions. And so the standards leave the full freedom to these instances to make all these decisions. The documents only provide information and insight to help and support these decisions, but they don't impose anything. And of course, the information that is given and the considerations that are made are not at all exhaustive. Many other additional reflections can be made that are relevant and may vary from country to country. Practically speaking, if there is anything that is normative in the standards, it's only the format of the reporting tables in Annex A. But in contrast to the other EPB standards, the tables here are open-ended and any information can be filled in, so complete freedom is left to the regulator. The advantage of having uniform tables is that it can facilitate the comparison of the national choices that are made between the different countries, the comparison between the different countries. One of the objectives of the documents has been to try to make actions and choices that in the past have often been to a greater or lesser extent implicit and automatic, to make them here explicit so that the processes and all stakeholders can be involved in a more conscious manner about all the discussions and steps that are going on. And the documents also constitute a kind of institutional memory, which is especially interesting for when new people are joining the discussions who have not participated in earlier decisions 5 or 10 or 15 years ago, that they immediately can get an overview of which kind of considerations come into play when the regulatory choices are being made. A further practical aspect is that the standards themselves, part 1, is very short, mentioning only the essentials, and the technical report, part 2, provides much additional information. And so both parts are best read in parallel, clause by clause. You start reading a chapter in the standard and then read the further detailed explanations on the same topic in the same chapter in the technical report. And the wording is generally for public authorities and regulations, but if private actors, builders want to set their own requirements, they can make good use of these documents and reflections as well. So this is a simplified overview. The outcome of the EPB calculations is a large number of final and intermediate results, which we call indicators. And in the regulation, they can be used for different purposes. The first one is the requirements. The second one is that these indicators can be rated. A judgment can be expressed whether a certain achievement is good or not so good. And there may be many other uses, for instance, in the private sphere, using the calculations or the results of the energy calculations for economic evaluations and optimization. All this information is integrated into the certificate and its accompanying report. So the indicator itself it is typically mentioned directly. For instance, it could be 123 kilowatt hours per square meter. And on a scale from good to bad, it can be rated. And usually there are colors and markets surveys have shown for the labels of products, domestic products like refrigerators, that consumers especially look at the color to judge whether something is good or bad. As soon as it's more or less green, they think it's good. And as soon as it becomes orange or red, it's considered as bad, independent what the value is or the class is. So this is something important to have in mind when designing the rating. Usually the requirements are also mentioned in the certificate if they apply and whether they have been satisfied or not, and much other information, in particular the recommendations for further improvement of the building in case of existing buildings. Then we come to the same slide, but with some extra information here. Sometimes the indicators are used directly, but sometimes for the purpose of the regulation, there is some intermediate additional processing where ratios are taken or the indicators are normalized to a certain reference. Can be the building size, but more advanced reference consumptions. And these often are tailored values, which are not fixed standard values that are the same for all buildings, but for each individual project, each building apart, they are recalculated depending on the features of that specific building. And we will pay much attention to that aspect in this webinar. The table at the background is very large, and so it becomes very small on this slide and is not readable anymore. I will quickly go through it to explain it. But essentially, the table is only conceptual to give an overall overview of the different aspects that are involved. And it can be used to indicate for which aspects, for which indicators, ratings or requirements are set. The headings of the columns you see here, what we discussed before, there is the indicator, the requirements, either for new or existing buildings, the ratings or other uses. And there is an additional column at the beginning called EPB feature. And I explain this with an example. The feature could, for instance, be the thermal insulation of a wall. And then there may be, for that single feature, different indicators, numerical quantities that can be used for that purpose. For instance, the thermal transmittance, the U value, or its inverse, the overall resistance of the wall, or only the resistance of the wall itself without the surface resistances. Or for some purposes, the temperature factor can be a good indicator. So even for one single feature, there may be several indicators. Then further in the table, we distinguish between the overall energy performance indicators, such as the primary energy use or the non-renewable primary energy use and other variants. And one may be used, this is just an arbitrary example here, for the requirement, and the other might be used for the rating to differentiate things, etc. Then we have a set of features that can be called partial energy performances of the buildings, for instance, on technical building systems, lighting, fans, systems expressed by their efficiency as indicator, or its inverse, what is called expenditure factor. And then we have a set of features related to the energy balance, like the heating needs, cooling needs, or floating temperatures, and the set of indicators related to the fabric, like the airtightness or the insulation. And there are, of course, an endless number of other features and indicators that can be considered. This table is only conceptual. Finally, at the bottom of the table, we have the products, which are covered by other regulations on the European level, notably for what concerns the requirements, the eco-design directive, and what concerns the labeling, the energy labeling regulations. And some of these products are building products and are also evaluated in the EPB, like boilers, pump, fans, the technical systems. Then there are domestic products like refrigerators and televisions, which are not as such in the EPB explicitly, and totally different products like vehicles, which have separate legislation on European level too. But so essentially, it's the same scheme where there are both requirements and labels, whether it's buildings or products. The next slide, you see at the right-hand side the same table with the range of the EPB policy and the product policy. And the additional frame here on the left are the EPB assessment standards, which can be distinguished between the calculation methods, the triangles, and the on-site measurements and inspections. So the calculation methods are many different standards, each of them represented here, well, just two triangles, but in total there are about 50 different modules, and they all produce on different levels, different outputs, different results, overall energy performances and intermediate values, which can be used in the regulation, maybe after some intermediate extra calculation. To do the calculations, the evaluation of the EPB, their input is needed, the choices from the annexes A, geometrical features of an individual project, some measurements like the airtightness can go into the calculations, especially in as-built files, control systems, system configurations, and product data. Here you also see an arrow. The airtightness, for instance, can be the object of an explicit requirement itself. So there are an endless variety of possibilities possible. Finally, at the bottom here, you have the product standards, which also use either measurements or calculations or a combination of both. And they are used in for the product policies, of course, for setting requirements and labels, maybe again with some intermediate calculations, like if you have boiler test data and pump data, you can have seasonal overall efficiencies. But of course, the product data that come out of these product standards are also an input for the calculation of the overall EPB of the building. And between those EPB standards and the product standards and policies in general, further mutual adjustment in the future still offers opportunity for improvement. Finally, another way of presenting things, this is the traditional table of the different aspects of the EPB with different modules, overarching aspects, the buildings as such, and the technical building systems, with then different sub-modules, and for each of them, on number 4, it's foreseen the ways to express the energy performance that it is being discussed. So for the overarching aspects, this is the object of EN ISO 52003. For the fabric and the energy balance, it's 52018. And for the technical building systems, it is embedded in the standards and technical reports for each of the technical systems. And these are mostly STEN standards. I mean, SEN standards at this time. So that brings me to the end of this presentation. I now give the word to Dick for the second presentation.
Good day, everybody. Thank you, Dirk. So I will move to the to the second presentation of this webinar. It's about the process of setting EPB requirements. First, briefly about my background. I'm one of the experts at the EPB Center. I have been involved in the initiation, preparation and the coordination of the total set of EPB standards in the last couple of years. I'm a co-convener of an ISO joint working group of 2 ISO committees that is responsible for the overall set of EPB standards at ISO level, and that's done in collaboration with CEN. So there are European ISO standards at the same time dealt with in that working group. I'm also convener of another ISO working group that also collaborates with CEN more on the building energy needs and the building fabric. And I could add that I have been for about 20 years responsible for the development and the further regularly updating of the national energy performance of buildings method in the Netherlands. So first about the objectives. Before we can elaborate the requirements, the pursued goals have to be identified. This can be a combination of several independent objectives. First, one of the most important ones is the healthy and comfortable indoor environment. And then second, of course, is also the energy efficiency. But there could also be other requirements added due to the goals, like the preservation of the fabric and equipment, for instance, to avoid degradation due to moisture. And other goals are also feasible. About the motivation of the choices for the requirements. There's a great variety of considerations that come into play. So, and having said that, I must stress, like Dirk also did, that public authorities have the full freedom to take the decisions. So what we present here is only to give a structure and to give suggestions and give a format that allows an easier comparison between countries. So economic considerations have often proven useful in the decision process because it maximizes the societal benefits at the lowest overall costs. And this is explained in a little bit more detail in this slide. So comparable economical strictness may lead to optimal results because there is a sense of fairness. The same economic effort is asked for everybody. It also better achieves an overall societal costs optimum. And there's less risk that the political decision-making is weakened by the economically unprofitable cases. But economic analysis also have limitations. For instance, there's usually no perspective beyond the time horizon of 20 to 30 years to make an economic evaluation feasible, whereas buildings typically last 50 to 100 years. So once the objectives have been decided, the next step consists of 3 elements. First, which mix of energy performance of buildings features and corresponding indicators do we want to choose? And then we can distinguish between the new buildings or equivalent to new buildings and existing buildings renovations. So for instance, we are thinking about overall energy performance of buildings, perhaps heating needs, perhaps the U value of a component, etc. The second issue is which ways do we choose to express the energy performance requirements. This can be a constant numerical value, can be a value, can be a variable value, and can also be a reference building or a formula approach, and that will be discussed later on. And which actual strictness do we need to choose? So cost optimal could be the driving force for the actual strictness, but at which cost? and could also be the goal to have nearly zero energy buildings, and etc. So the first two questions are strongly technical. The last one is very policy driven, so that mainly societal, political aspects to that. And of course, there's a strong interaction between these, so you cannot avoid speaking about one when you are dealing with the other. So let's go first to the first question. What requirement mix? And then, well, for which features? And then if you have a feature, you can have different indicators, as Dirk already explained. So also you have to ask yourself which indicator. So let's look at considerations for new buildings. Definitely you want requirements for the overall energy performance of the building. That's the holistic approach. It stimulates all aspects of the design while leaving a maximum degree of freedom for the choices. So for instance, primary energy per square meter floor area. Could also be additional partial energy performance of buildings requirements. For instance, as a function of objectives like we want to reduce the energy needs first, or we want to focus on long-lasting components, for instance, the fabric, to have them at least at the highest possible level. So thermal insulation or air tightness. And you have the discussion whether to go for a limited number or a larger number of partial requirements, because there's a risk if you have a large number of these partial requirements that you come into conflict between these requirements, and specifically that you have a conflict between the partial requirements and the overall requirements, and that would damage the holistic approach. So sometimes you see partial requirements to be applied only as a safety net. So requirement mix for new buildings. There are some details, some introductions given in the overarching standard, the 52,000 part 1. In the informative annex H, you find a proposal of indicators for the assessment of nearly zero energy buildings. And actually this proposal contains different steps from decreasing the needs and decreasing the energy use and optimizing renewable energy use. And you find also default choices in the annexes B, the annexes where the national choices are spelled out in the two standards we are discussing today. When we come to requirements mixes for renovations, it becomes much more complex, because in case of renovations, you have often restricting boundary conditions and less design freedom. So consequently, the overall energy performance requirements based on the holistic approach are not always evident. Some components might not be changed and might even be unknown. So that makes it difficult to deal with the overall energy performance requirements as you would now do for new buildings and new building designs. So therefore, you see often requirements on component or element level, or requirements on a combination of elements, which gives you already more design freedom than the requirements on a single component. But it's much more challenging to formulate which kind of combination of requirements you want to have in a regulation and to set the level of it, the value. So usually you find in a regulation quite a long list, but in practice only a few of the requirements apply to each individual project. Once the features and the indicators have been chosen, the next question is to go for constant or variable numeric requirements, because often a constant value doesn't lead you to this desired comparable technical economic strictness. This depends on the indicator. For instance, let's take a simple example, the thermal transmittance of a single component. If you have a constant requirement, that value, that's usually okay. But if you go then to a mean thermal transmittance for the whole envelope, you might need a variable, a tailored requirement value. Look at these two buildings. So assume that in both buildings you have chosen identically the best possible technology for insulating your window and for insulating your opaque parts, the facades and the roof. And on the left you see a building with only the front facade exposed to the outdoor, and to the right you see the same the building with the same technology, but now all the surfaces are exposed to the outdoor, which means that in the left case it will be much more difficult if you realize that the thermal transmittance, the U value of the window, is not as good as normally with the best possible technology as the one for the facade. It will be much more difficult to achieve a low mean value for the overall thermal transmittance, for the mean U value in the left case compared to the right case. And similarly, you could have this, the same said about the overall energy performance or the heating and cooling needs. And Dirk will go into more details about this later on in his presentations. About the way to express the energy performance requirements, you could also choose a ratio as an indicator, because a ratio can provide insight or greatly ease the communication. Complex things can be summarized in a simple number. So variable value requirements can be expressed as a constant value itself if the indicator is a ratio. So then you no longer need a variable value requirement, but you have a ratio which is a constant, but in the ratio you have the variability embedded. Often with a ratio, you do not only have an indicator, but already immediately a quality indicator. So you can directly use it for the rating. And another advantage of using a ratio is that you focus on differences between energy efficient designs or measures. So you are less distracted by differences between different models for the calculation or differences between the model or measurements. Well, a challenge is that the indicator needs to be adapted over time to reflect technical and economic evolutions. So an example to illustrate the ratio. For that, we come back to the example which we showed before. So at the left-hand side, the mean U value is dominated by the windows, and the right-hand side with the large exposed envelope, the mean U value is dominated by the opaque construction. So if you now introduce a reference building, so here a reference building which has the same size and shape as your actual building, but you have here a reference U value for the facade and for the window. So on the left-hand side and the right-hand side, the same reference U value for the window and the opaque elements. But the ratio or the proportion of the two is of course different between these two, and this means that if you now not go for a mean U value requirement trying to be the same for these two buildings, you go for a ratio. So you take the ratio of the mean U value of this building and of the reference building with the same size and shape. You can have a fixed, constant requirement expressed in this ratio, the mean U value divided by the reference mean value. And more details about this are given in the next presentation again. Now the third question we have to answer is about the actual strictness of the requirement. Well, as we said before, this reflects the societal and political ambition level. If it's based upon economic considerations, there are several hypotheses to be set, and hypotheses, for instance, about the future energy price evolution have an important impact. There's some possible cost scenarios. So it could be the anticipated private market price, which is guiding the choice, or macroeconomic energy price scenarios in which, for instance, external costs are incorporated, but in which subsidies and taxes are excluded because they are covered in the overall macro view. Another interesting possible cost scenario is to go looking for the equivalent costs of the most expensive large-scale form of renewable energy, which is accepted in the society as an alternative. So any other technology that would be cheaper than this accepted alternative, which might be more expensive, would be already a positive contribution to a cost-effective progress towards a more energy efficient building stock. So as you see, there are several considerations here, and of course there's much more to be said about this. But in my presentation, I just go just for one other subject which I like to touch upon before I end this presentation, and that is the principle of assumed or the actual presence of a system. Remember that we said in the beginning that one of the important and therefore very probable policy objectives of each country is to have healthy and comfortable indoor environment in energy efficient buildings. Well, let's again look at a simple building. Here on the left side, you have a building with a heating system, which is comfortable, but at the cost of the energy performance. The heating costs energy. Then we go to exactly the same building here to the right. It's exactly the same building, but assume that there's no heating system present here. So it might be uncomfortable in this building, but you have very good energy performance because you do not use any heating in this building. So now comes the important question. Is building B a more energy efficient building or is it not? So there's a policy choice for these two buildings. What would you do? Would you go for, in case B of this building, if you have no heating system, to assume a default system, heating system, or would you not? If you do not, you do not take into account that you have uncomfortable condition and you would favor a building with a insufficient system to give you a healthy and comfortable indoor environment. Would get a high energy performance, and that's not what in most cases you would like to see. So in many cases, it's just assumed, the regulations say that you assume a default system. And the same could be done for cooling, for lighting, for domestic hot water. And it not only if a system is not present, but it also goes if a system is undersized. So for instance, if you do an energy needs calculation for heating and cooling, you would find out that if you introduce in this calculation the maximum power of the system, it would come out as a result, if you apply an hourly calculation method, the subject of the next webinar, by the way, it would come out that you have temperatures in your building which are not according to your comfort criteria. So then you would have to deal with that. Okay, so that concludes my presentation, and I will give the floor back to Dirk, and I'll come back to you later for my second presentation. So I'll give the floor to Dirk.
Okay, thank you, Dick. I will now give some examples of ways how EPB requirements can be tailored and why it is important. Dick has already illustrated, and there are some more examples coming now. This figure will come back a few times with a few variations, so I will take a minute now to explain it. What you see here is the total energy performance per useful floor area expressed in kilowatt hours per square meter as a function of the so-called shape factor, which is the ratio of the envelope area to the useful floor area. And each of these little crosses here, there are over 200 of them, represents a single individual real geometry of a dwelling, for which the energy performance was calculated given a set of technical hypotheses. The buildings on the right with a high F factor, a high shape factor, are typically small detached buildings, dwellings, also bungalows. Whereas buildings on the left-hand side of the scale with a small shape factor are very compact geometries, either because they have a very large volume, very large buildings like students' homes or elderly homes, or when individual apartments or studios are concerned. As Dick has illustrated in his previous presentation, sometimes they only have one facade which is exposed to the outdoor, and then the envelope area is very small compared to the floor area. What we also see here are 4 larger dark blue crosses. These were the points that at the time were, or the dwellings, the geometries that were used to do the cost optimal calculations. I should say this has all been done with the Belgian EPB methods more than 5 years ago in the meantime, at the state of the methods at that time. And a conclusion of these analysis on the different cost optimal geometries was that the set of technical measures which comes out as economically optimal is very similar in all 4. So as a first assumption, we can assume that applying this same package of measures to any other geometry gives reasonable requirement, both in terms of technical strictness, that all projects are treated in a similar manner, and in an economic aspect. So we see here that applying this to the more than 200 geometries, these are the last variation, with points being above 120, others below 60 kilowatt hours per square meter, so a factor of more than 2. And we see a clear tendency that when buildings get less compact, their consumption will typically increase, of course, because their envelope area is larger compared to the floor area. So setting a constant requirement, the same for all buildings, which is very easy from the point of view of the regulation, means that there is a very uneven requirement for individual projects. The ones here, the more compact ones, will satisfy automatically the requirement with a moderate package of measures, and they could even relax their efforts, energy efficiency efforts. Whereas less compact buildings on the right will have to do much more effort to reach the same constant value. and so they will go well beyond the cost optimal. Whereas buildings on the left, if they would reduce their efforts, they will not fully exploit the cost optimal potential or cost effective potential for their project. So on an overall societal level, it's not an optimal distribution from an economic point of view either, to have a constant value requirement, if it would be the average value as shown here. But there is a danger that in the political process, in the discussions, people will come up with these practical examples, and a poor person, poor family living on the countryside, building a small detached house, will say, look, I am not very rich and I build a small house, but I have to do tremendous efforts because the standard technical measures are not at all sufficient. I need to do tremendous efforts to lower to below the requirement. And then politically, it might be decided to lift the requirement to a higher level, which then applies to everybody, to all projects and buildings and shapes, and that will be even much less efficient. Here you can see the same cloud of points as before, plus 3 other points for other packages. I will not discuss it in further detail, but it shows that even if the requirements get stricter and very strict low requirements, you still have similar tendencies, and variable requirements are generally speaking still good to have comparable strictness for all projects. Now, how do you do this practically to tailor to each individual project? Roughly 2 main approaches can be distinguished. One is called the notional reference building, where the requirement is the value of more or less the same building with a predefined set of reference hypotheses, as Dick has already illustrated for a small building, and as I will show immediately once more. The other approach is to use a mathematical formula where the requirement is then a function of building variables like the size and the shape and ventilation rate and other possible parameters. And this mathematical function can be very simple, linear, or complex with exponents, etc., to fit well with the calculation methodology. This is again another illustration of the notional reference building approach. You have your real building with your real set of measures, and if you calculate the energy performance, you will get your indicator, your value. And then the notional fictitious reference building uses the same size and shape, but applies a set of reference measures technically, but also, for instance, for the size of the windows, which could be optimized. And then the calculation is redone, and a new value is obtained as a result, which becomes a reference for the rating or the value for the requirement, and the real value should be lower than the requirement value, while leaving full freedom in the actual building to apply any other set of measures that still satisfies the requirement. This is another way of presenting this. So the development of the method in the case of a notional reference building is essentially the definition of this set of reference hypotheses, which are then integrated in the software, and when a particular project is calculated, specific features of that project will be used to do the calculation on the virtual building, resulting in the requirement. For the formula approach, during the preparation of the regulation, there is a much more preparation work to do, calculations and analysis, but it results in a formula. And the 2 ways can be distinguished, more analytical and statistical. I will not discuss it here in detail, but the end result is a formula which is embedded in the regulation. And then for an individual specific project, again, the same project in features can be extracted, can be considered in integrated in the formula, which is a quick calculation, then and immediately gives the requirement value or the reference value. In the past, there has been a lot of discussion between these two methods, which one is best, but actually, if you analyze them carefully and you apply them to practical examples, it should be said that if the starting point, the set of reference measures and hypotheses, if these are equal in both cases and the work is properly done, then the end result, the numeric value of the requirement, is usually also almost the same. There may be a little bit difference because, for instance, smoothing as a result of the formula approach, but usually the difference are rather small. And so, although there have been huge theoretical discussions, in practice, both methods can work equally well if properly done and give satisfying results. So which variables can be considered for tailoring? The building category, is it a dwelling or an office or a sports facility, etc.? This will of course determine occupation densities and internal gains, and as a result the requirement will be different. As indicated before, geometrical features of the building itself, the location, if in a country there are different climatic zones that will influence, or the altitudes above sea level sometimes is a variable which determines the external environmental conditions, temperature and solar radiation, and then the indoor requirements and services. What are the temperature set points for heating and cooling? What is the ventilation rate, illumination level, how much domestic hot water is needed? All this will determine the numeric value of the requirement or the reference. And also sometimes not all energy carriers are available on all locations. That may be taken into consideration, as well as still other variables. To round up, I quickly say something additional to the standard. So this you will not find in the text. About this mass calculation, these clouds of points that I have shown before. It can be very useful and provide insight for several purposes. First of all, it can be used to check the EPB assessment methods themselves, apply them to a variety of cases, and then see if there are no, oops, I apologize. Here I'm back on the right slide. So to verify if there are no anomalies, if in all cases the results are logic and reasonable, and so whether the calculation method itself is robust. Then, as I have illustrated, they are very useful to check the requirements over an entire range of possible geometries. Is it more or less equal, the technical strictness and economic strictness for each project? Or if there are some needs to take extra measures, how much more measures are needed? And is this acceptable politically and societally? And if there are anomalies, you can analyze what is the cause, and maybe you will still say it's acceptable. An office building with a lot of glazing and no solar protection, for instance, if it has a lot of overheating and cooling needs and cannot satisfy the requirements, you can still say, well, that design is not acceptable. It should have solar protection devices or reduces solar gains in another way. And so this analysis becomes all the more important as the requirements get stricter and stricter over time, because then the leeway to do better, both technically and economically, is much more restricted. Finally, it can be used also for cost optimality calculations in an automated manner, or maybe still other purposes. And I will show a slide later on. Just a practical suggestion. For the calculations, it takes a lot of effort to automate this work, and you need to collect ideally a representative sample of real geometries over a wide range outlying also outlying cases to check the robustness of the method. So it's quite some effort, but it can be used for different purposes and may be worthwhile. And this is an example to round off about cost optimal calculations, where for one single geometry, thousands of sets of technical measures have been calculated automatically, and you see the energy performance on the x-axis and the total life cycle costs on the y-axis. And there you can clearly see what's cost optimal and also what are technologies which can become cost optimal in the future and can be stimulated, etc. So it can provide a lot of insight, this kind of analysis. This ends my presentation, and I now give the word back to Dick.
Thank you, Dirk. I'll quickly continue with the next one, trying to catch up a little bit in time about rating and certificates. So if you have a numerical indicator, whether it's overall or partial, it doesn't tell you automatically what is the energetic quality. So you need a reference. What is a good energetic quality and what is a poor energetic quality? This means you have to come to benchmarks in order to rate the building or the component. So let's look at overall energy performance. Take the actual level, put it on a scale and compare it with, for instance, 2 reference points. And then you could also add the requirement on the same scale, and you have the rating. The same could be done for a component. So any indicator, for any indicator, you could have a scale, 2 references, and you could have the limit value plotted in as well. But for many partial indicators, there is no requirements. These are just for information. If we zoom in on these reference values, you see here the same picture as you saw before. You could say, okay, I take as a first reference 0, and then I have only 1 reference value. So in fact, you would still have 2 reference values, but the 0 is a kind of an implicit reference value in this case. And the next step is, here you see the one with the 0, the single reference value. You could have the actual level expressed as a ratio. So you could take the reference value, divide your actual indicator value by the reference value, and then you would have a 0 to 1 scale. And in this example, it will be 0.0 as your indicator value. And the advantages have been introduced in the previous presentations. So if we look at the types of energy performance rating scales, there are many options possible. So I showed you the 2 reference values or the single reference value, a continuous or discrete scale. And if you look into the standard, you'll find 2 methods, which means that 2 of these methods are fully described. But jumping to the bottom of the slide, others are also allowed, just to make sure that you understand that we're not imposing anything in the standard. It is up to the national authorities to choose. But for instance, the first method, so the 2 methods are fully described. The first method was already used in many countries. And the second method is a further developed, advanced version, which was recommended in a dedicated European study. And these will be shown on further on. But first, if you have the rating and the scale, you still can have it graphically represented in various ways. And you see here 2 different types of representation of the same classes. So the next slide uses this representation because that is the one which is proposed in the standard to use. So the first method uses this graphical representation, and it has 2 references, one on the average building stock and one on the minimum energy performance required for new buildings. It's allowed to expand the first class A, by A+ to A triple plus. So this method uses 2 reference points, and it also uses a more or less linear scale. And in the standard, you have specific variations described, which you can specify in the annex where you make the national choices. Method 2 uses the same graphical representation, but now you have only a single reference, and the other difference is that you have a logarithmic scale, which is shown on the next slide. So here you see, instead of a more or less linear scale as in method 1, you have a logarithmic scale here, which is more appropriate actually, because in practice it will be still much harder to come to more energy efficient buildings the more you go to the left to the already low energy building classes. Then the last part is of this presentation is about energy performance certificates. So you have the energy efficient rating, and they are recorded on the certificate. And there's often a misunderstanding that this EPB standard deals with certification of the energy performance of buildings. Well, that's absolutely not the case. It deals with the energy performance certificates. So not the certification process, the protocol, only about the content on the EP certificate. And typical sections on the EP certificates are information on the type of EP assessment, whether it's measured or calculated, type of building, type of indicators, which protocol is used, and of course the report of the actual assessment. So what's the input or the main elements of the input, main characteristics of the method, the output, the energy label, and recommendations for improvement methods. In the technical report, we find different details of the energy labels where you put your energy rating on. So here you have the example of method 1 with the actually with method 1 or method 2 with this graphical representation. There's another example which allows for 2 different classes in your case. So it could be a rating for the as-built situation, or a rating for the building in use. So for instance, a measured rating. And then to show you a completely different rating is the continuous scale, which is also an option that is explained in the technical report. And as I said, these are just options you can choose. And this concludes my second presentation. And I'd like to give back the floor to Dirk for his last presentation before we go to the questions and answers session.
All right, thank you, Dick. I will now go very quickly because we are running out of time. So this last presentation will give a few highlights of the standard EN ISO 52018. Okay. Here we see the title. So it concerns indicators for the partial EPB requirements related to either the thermal energy balance, so the energy needs, or the temperatures, and related to the fabric features. Part 1 only gives a brief overview of the options and reporting tables, and Part 2, the technical report, gives further extensive explanation. I will now go quickly through the following slides because they are essentially much repetition of what I said previously. So the processing happens after all the calculations are done, but this standard deals with the output partial out indicators related to the building fabric and to the energy balance. The same reminder, the same warning as before. The standard does not impose anything on regulators. They have the full freedom to make their choices depending on the national needs. And both documents can again best be read in parallel. And in the technical report, part 2, in a systematic manner for each feature, in as far it's relevant and applicable, the possible motivations are discussed, what kind of indicators can be used, if there is an issue of comparable economic strictness, thus having constant or variable numeric requirements, any practical points of attention, sometimes testing for airtightness, for instance, may be relevant. The difference between new construction and renovation, where different issues may apply, and exceptions which should be allowed or not. So we will not have time in this presentation to discuss each of these features in detail, but they relate to the energy balance, the summer and winter thermal comfort, so the floating temperatures, and the energy needs for heating and cooling, or a combination of both. And requirements can be set for them, and depending on the purpose, whether it's mainly indoor environment or energy efficiency, or still other options are possible as motivations, one or the other feature may be more appropriate. When it comes to the fabric, there is the overall thermal insulation of the envelope, the insulation of individual components, thermal bridges, an overall rating, energy rating of the windows, the airtightness of the envelope, and solar control aspects. So I will not discuss all these features in detail because we don't have time. But maybe one general point of attention is to find a good balance in the regulation between winter and summer aspects, especially in early regulations in the 70s, 80s, 90s. We have seen that in Middle Europe, focus was on the largest consumption, that's space heating. And then there were one-sided regulations targeted on this consumption only, which sometimes resulted in designs which maximized passive solar heating in winter without taking into consideration the effects in summer. So have no solar protection, shading devices, etc., resulting in overheating, severe overheating problems as a result indirectly of the regulation. So this can be avoided by setting explicit requirements or for the overheating indicator or for the cooling need, even if there is no cooling applied, or include a fictitious coolant consumption in the overall EPB indicator, which is also discussed illustrated in the standard, and I have some slides later. And the same holds true for unheated buildings in warm climates, of course, vice versa. Here you see a similar graph as before. The difference now is that here the heating needs are shown per useful floor area, and we see again a similar tendency with even a larger spread by a factor of more than 4. And of course, this explains to a large extent the variation we have seen on the overall energy performance before, because the heating is so dominant in this climate for which calculations have been done. I will not discuss in more detail the variations, but a single line, I should stress, a single linear line, which would be a tangent to everything, is not necessarily a good requirement, because there may be other aspects like ventilation rates, etc., which do not depend on the envelope area, but which may vary from one building to the other, and which may explain why there is some variation even with the same set of technical measures. Next slide, you see that you can again explore different sets and see what kind of measures would be needed to satisfy a certain requirement. These are a few 10,000 points taken from the regulation in Flanders, the dark ones during the years 2008 and 9, and the light ones 2010-11. So for every project after construction, an as-built dossier is submitted in an electronic database, and the results are analyzed and visualized here. We have again the heating needs per floor area as a function of the capacity. That's the ratio of the volume to the envelope area. And so we see for large compact buildings that having a constant value as a requirement for the heating needs would have no impact, because just applying the insulation requirements and doing nothing for ventilation and the efficiency of the ventilation system and the air tightness of the envelope, all these buildings automatically satisfy largely such a requirement. Whereas other small detached buildings can have much higher consumptions and would need to do tremendous efforts to lower to this average constant value. It's technically possible, and you see that there are many points below the line, but nevertheless, it's still a very unequal requirement. And people in these situations will often complain and ask exceptions, which can cause, if they are allowed, they can cause a lot of administrative burden. A similar thing can be said for the mean value, where the mean thermal transmittance, I mean, if you set a constant value, it may not be a very equal requirement, because you also need to make some allowances for the transparent elements in addition to the opaque elements, which have very different achievable U values. And if you make the analysis, it will show that a line not going through the origin, but with a certain slope, may be an optimal value. And there still may be a cutoff. You will not become too lax, of course. You do not need to have your entire envelope to be with windows. A certain fraction will suffice. For the sake of time, I will now skip the last slide on how fictitious cooling could be integrated in the overall EPB indicator, but you can find this back in the technical report. So I skip this, and we can then go to the questions. So we cannot answer questions right now, but if any time in the future, tomorrow or next week or whenever you're looking these documents or other EPB documents, you can use the contact form on the website, which is on the right-hand side of the menu at the top. And there you can submit your question in writing, and we will give you an answer. So thank you for your attention, and then we can now answer your questions.
Thank you. So let's start with the questions. So one question we received has a link. So please, Dick and Dirk, can you check the chat? I sent you the link so you can open the link, and so you can answer the question, otherwise it's not possible. So what do you think of the graph? So let's open it. It's difficult for the rest of the audience to understand, actually, if you cannot see the link. Did you open it?
No, I can't find the link, actually.
I sent you a message in the chat.
The chat box.
In the industry embodies as the
Okay.
better building partnership frequently show this graph.
Yeah.
What do speakers think of this? Could EPC become better representatives of building performance? Thank you. So if you can also describe the graph a little bit for the audience.
Well, from my side, I would like to say that it's not obvious because there is also little or no explanation with the graph. It's not obvious for me to give instantly a reaction. I would need to study the graph in more detail to properly understand it and be able to give well-founded comments.
Yeah, I understand this. So let's move with another questions, maybe. Are there particular contexts for which you will recommend applying or not a reference building and formula principle? I think it's for Dirk.
Okay. So as a general rule, I would not have any recommendations that would be applicable to all different climates and regulations. I think it has to be evaluated carefully on a case-by-case basis, which feature, which indicator you are considering, and then do a careful analysis whether, depending on the policy objective, of course, if you want comparable technical and economical strictness or not, because this is the basic policy choice that needs to be made. But once this choice has been made and it has been chosen to go for fair comparable strictness, then further technical analysis is needed, applying it, for instance, to a large range of geometries, also do an analytical analysis to see for a given feature and indicator whether a constant value or a variable value is appropriate. And then the choice between notional reference building or a formula, a priori, since if they are well done, they both lead to the same results. There is no reason to prefer one to the other. For practical purposes, the reference building may be more easy to apply if you have complex calculations which are difficult to fit in a simple formula. But for other aspects like the mean U value, a simple formula probably can be very satisfying. So it's difficult to formulate, from my point of view, general recommendations in one sense or the other. I think on a case-by-case basis, it needs to be studied and evaluated what is the best solution.
Yeah, maybe I can add that for the reference building approach might be a choice preferred when you allow in your country different tools for the calculation. So if you're using different calculation software tools, then in the reference building approach, then you cancel out some of the differences between the models.
Yes, that's right. I agree.
Okay, let's move another one. Are there any cases of collaboration with local authorities in the domain of EPB?
I
don't know, Dick, if you want to answer on behalf of the center.
Yes, with regard to the EPB center, there are close contacts with local authorities in that aspect, that we ask local authorities to give us feedback on the information that we provide at our website. And we get many questions on the basis of that by local authorities filling, representatives from local authorities filling in the contact form, asking about more information and so on. And this gives us the possibility to give a more tailored support to the countries where they need it. Having said that, there are still a number of white spots, so to say, there where we would like to learn more how our, to what extent our support provided at the website is adequate. So we keep saying that please feel free to contact us if anything is unclear at the website or in our communication.
Okay, thank you. So another question, which is for Dirk. You mentioned that further mutual adjustment between EPB standards and policy and product standards and policy would be possible. What do you mean practically? Can you give examples?
Yes, for that purpose, I can go back to my slide. Just a second, I am moving to the slide that's concerned. We're almost there, I think. All right, it is this slide. So here on the top, you have the EPB standards and the EPB regulations. And on the bottom, you have the product standards and the product regulations, like eco-design and energy labeling regulation. First interaction between the product standards and the EPB standards is that the testing data or the calculated product characteristics are used as an input to the EPB assessment of the entire building. And so sometimes there is still a need to have better adjustment, mutual adjustment between the two standards. For instance, to make a robust assessment of how a certain system or product will behave in a specific building context, there may be a need for an additional testing point, for instance, or even for relatively new products, completely new product standards to identify and quantify in a uniform manner these characteristics. So that's first example how better interaction and collaboration between the two sets of standards can still be achieved in the future. A second example would be, as a matter of principle, I have indicated here, you have a triangle for a certain calculation, for instance, the boiler efficiency. You see the figure 1. I have repeated the same figure 1 here. In the product regulations, you will also have overall indicators that combine different testing points, etc. As a matter of principle, so until now, these methodologies are developed completely independently from one another. But as a matter of principle, it could be considered that in the future, more interaction between both is studied and maybe more convergence can be achieved, where a more general method from the EPB calculation, which can adapt to the specific boundary conditions of the building, its size, etc. This is not possible in product policy, but still the same calculation methodology could be applied with standard values, for instance, for these building specific features. And the third example would be more on the policy level. Now for the product data in several of the member states, we see that databases have been developed to a greater or lesser success. At the same time, now we see that for the products on a European level, the energy regulation foresees that a database there will be developed as well, which is due or which is already under development and which will become operational somewhere in the near future. So in the first instance, this database is only about, as far as I understand, essentially the information which is on the product label. But so the same product, a boiler, for instance, might then be in different databases on a European level and on several national levels. In the further future, there is an opportunity for further development to have synergies so that, for instance, more data at a later stage could be integrated in the European database, which then could immediately be useful for the EPB calculations as well, like the standard testing points, etc. In terms of development, we can think the first set of EPB standards some 15 years ago, we had many different individual calculation standards, but mutually they were not always well adjusted among themselves. And then in the second development, about 5 years ago, all these EPB standards were made much more coherent and consistent so that they work well as an ensemble and give all the required outputs. A third future step would be that we still coordinate more between the EPB standards and products and policies to increase both effectiveness and productivity of the regulations. So that are still potential developments that are possible in the future. That ends my answer.
Thank you. So we have a few minutes for one last question. So this is for Dick. Is there an EPB standard on cost optimal requirements?
No, actually, there's not an EPB standard on the cost optimal requirements, but there is an EPB standard on economic evaluation procedures. So if you go to the EPB Center website, you'll find it under the overarching subset of standards, because it's an overarching topic. So in parallel to the assessment of the overall energy performance of the building, you can use this standard for the overall economic evaluation procedures. And this is also the standard which is mentioned in the guidance given by the European Commission on the cost optimality studies for the countries.
Thank you. Maybe we can answer another one. You mentioned this for both of you, I think. You mentioned advantages of using a ratio for setting variable and tailor requirements. Isn't there a disadvantage that the indicator gives no quantitative information, for example, on the overall energy use? If you could be brief, as we have just a few minutes.
Yeah, should I start? Okay,
Yes.
so brief. Yeah, well, so I know in the past, for instance, in the Netherlands, there was the discussion. Well, actually, we are glad that you do not give an absolute number on the energy performance, because that would confuse if you compare it with the metered energy use, which is affected by the actual weather and the actual use of the building. But having said that, nowadays we actually would like to see also the absolute energy use on the certificate. So I guess it will be recommended to have not only the relative number, so the ratio or the comparison with reference buildings, but also an absolute numbers.
I have nothing to add from my side.
Okay, great. So there's actually another one coming in right now. If there is a heating system, but the family is in an energy poverty and does not turn it on, or if it is turned on occasionally, intermittent heating.
Could you repeat quickly the question?
If there is a heating system, but the family is in energy poverty and does not turn it on.
Yeah. Well, yeah, that touches upon the difference between measured energy performance and calculated energy performance. Actually, in the measured energy performance would then in this case be very good because you use less energy, but it's usually the measured energy performance is in one way or another being converted to energy used under standard conditions. So you assume that there's a standard way of using the building, depending on the type of building, depending whether it's an office or a residential building or whatever. And then you would cancel out the differences by the different use by energy poor people and energy spoiling people. Yeah.
Maybe I can briefly add that the difference between the calculated and the measured energy is usually described with the words operational rating and asset rating. Where operational rating, you look at the real behavior of the building and its users, and the asset rating will make abstraction of the users and only value the energetic quality of the building and its systems.
Thank you all so much. So I would like to close the webinar. I thank you to the panelists and the people who participated. Finally, I remind again the next webinar, the fourth of the series, which will take place on 26th of May. You will be able to register through the link on the Build Up event very soon. So thank you again.
Thank you to all the audience for their attention.
Thank you all, and also you, Julia.
Thank you.